Welcome to the video on binary search trees, and to begin I'll be just showing a quick little overview of my binary search tree header file and my CPP file. The source file is just basically my interface of how I incorporated it, and I used like filed input, output, but the core, obviously the delete, add, and all that stuff, and print in order, out order, those are all in my .h and CPP files. So that's the core thing. I'll just do a quick overview of, and then I'll get into what a binary search tree is and how do we create it, add nodes, delete nodes, everything like that. Okay, so this is my BST class, my binary search tree class. We have my private section is here, and I have a node. I decided to make node private because I just didn't want to require any users to, need to use nodes. Like, if you just take these two files, you don't need to input node in source anyway. Like, there's no node written anywhere here because it's all private here. And I have a node, I have a remove root, I have a remove normal root, node, then I have add leaf, and all this stuff, display, and all those things. And here, this may be a little bit curious because it seems a bit redundant because I have copies. Basically, I have add leaf private, add leaf return node, find smallest key, all those things. And this is just to further, add to the whole thing of not requiring anything in the source file to have node as an argument. So basically, if I say I want to add a leaf, I'll add a leaf here. This is the public version, which is what will be called in the source file. You just insert an integer, that's it. And then that calls the private version, which requires the root node. But because the source file doesn't have a root node, it wouldn't be able to do this. So I just thought this might actually make it easier and read easier in my source file, where I would just have to put in integer. And then that will call the private function, which requires the root node, and that's where it'll begin. So let's just take a look at the definition of, this is just a random sort of binary search tree. What we have is, we have a root node right here. Oh, that's pretty, it's, yeah, root node right here, that's 8. And that's basically, if you have like maybe inputting files, it may be the first, so if 8 was your first data point, that's what you would have. Then you would have a left and a right child. And the main thing that separates the binary search tree from a normal tree is that it's ordered in a very specific fashion, where, of course, as you enter new data, it'll be put in as a leaf, of course, but the left node is always smaller than the parent node, and the right child node is always greater than the parent node. So again, the parent, then you have the left child node, which is less than the parent node, and the right node is greater than the parent node. Then we keep moving down, and it follows the same thing, and this is called a leaf. The same thing for normal trees. This is just a brief overview. These are all leaves, whatever. And I guess if you want to say this way, these are both null here, null here, null here. They all have nulls, where there's nothing. So now this is just a basic, this is something I found online, but if we want to make our own thing here, this is the text file numbers that I use in my project right now. So I just copied them here, so we don't have to keep this up. But this is what this program is actually using to input data. So let's get back here. Now let's look at the add leaf. Well, okay, you would first create a leaf. Creating a leaf is just, it accepts an integer, creates a new node, and the key of that node will be the data, with the node data, which will be the key, the integer. So in this case, it'll be the first one will be 91. Then it just makes a left and right children being null, because you want them to be null for the future process, because all of the recursive functions loops until the left or the right is null, and that's where you start inputting data. Because for this tree, the reason why it's called add leaf and not just add a node is because you're always going to be adding it as a leaf. So yeah. Then we get to the add leaf, and of course we discussed this earlier, where it calls the private function, and this is where the real add leaf is. So first thing, it checks is the root null? Is there nothing in this tree? And we look at this, and yes, there's nothing written down. So let's write down 91. Let's actually make that text a little smaller. Maybe 48. Yeah, let's put that 91 there. So now we've done with this. We've got a 91. We've crossed that out. Now we're going to do 9. So now we're going to check. We go back to the beginning. It calls it again. Is the root null? No, the root is now 91. We've already created it. So now we have to look at the else statement. Then we look, is the key, which is what we're inserting, is that less than the pointer key, which in this case it always starts as you can see, root. So we always start the root, and the reason why it's not always root is because if you do recursive functions, it'll eventually, it'll start calling itself, and then you'll maybe call left and right. We'll get there later. So if key is less than the root key, which is what we have right now, which is 91, because these are all integers, then you call this. And that this is true, so we call this, and then we have an if within that. If the left of your root node is not null, then you keep calling it recursively, just keep doing it. But if it is null, which is if this is true, then if this is false, that means it is null. It is null. Then we do the else statement, and the left node, because it's null, we just make that the create leaf, and the create leaf is just returns the node. So the left node becomes that node that we created with in this situation 9, and so yeah, that makes the left. So this goes directly left. So let's cross that out, and let's type in 9. Now we look at 4. So 4, we do the same thing. We check again with the root to begin with, and let's go back here. Is it null? No. Then we check, is 4 less than 91? Yes. So we check this one. Is this null? No. Then we check, is 4 less than or greater than 9? If it's less than, we look at the left, that's true. The left is the first one, so left is true. Then we see, is left of 9 null? And it's true. So we create a little thing there, and we make 4. So basically that's the key thing here that we need to remember for this. It's just recursive checking, and this is how you would do it in the code, and this is how you would do it there. And it's a very simple little statement there. Also, if it's not greater than the key, if it's not less than the key, then it's equal to the key. So naturally, it would say that it's already been added to the tree. This is just a thing, which we'll come to that later as well. And let's look at. I also got 56. 56 is less than, same thing as number 9. We just go left. But this one is now not less than 9, it's actually greater than 9. So now it's the same principle, but because at this point we've looped it and it's done a few iterations where the recursion has gotten to a point where this pointer key is 9. So is 56 less than 9? No. Is it greater than 9? Yes. So now we're looking at the right side. Is the right of 9 null? Is it not null? And that's false because it is null. Then we just directly create the leaf. So this is what it is. If 9 wasn't null, then you would just keep looking down and you would traverse the tree that way. But because it isn't, let's just add the 56 here. And now I think we've got the grasp of what this is. So let's just quickly, let's go a little bit faster here. Let's look for 8. 8 less than, greater than, so it goes right to the 4. Let's put an 8 here. We have an 8 there. Then let's cross that. We don't want that big of a line. Sorry. Let's cross that 8 out. Now we're looking at number 9. 9 we look less than, and because it's not less than or greater than 9, it means it's equal to, which is where this statement would come into play, because it's not less than the key, it's not greater than, it is the key. Naturally it would be it. So it's already been added. So we don't do anything, we just cross it out. Then we look for 105. 105 is actually right at the top, it goes right. So we have 105 here. Yeah, simple as that. Then same thing applies for all sides. It just keeps traversing the tree left or right until it reaches the null point. Then we look, is it greater than 91? Yes. Greater than 105? Yes. Then we got 999. So let's put 9. Then again we have a number 9 again. So it's just a double, making sure that we know that it's boundary search trees. I mean, all trees generally don't want to have duplicates, but it's especially important in a boundary search tree because it is very dependent on, you know, the order. So let's cross that out, and then let's do 71. We can find this place. Oh, let's first draw the line. It's less than this, but it's greater than this. Then we check. It's not less than 56, so it goes right again. And there it is. So now, so let's look at this this actual implementation in my little program here. Let's print the tree, and let's compare it to what we've come up with here. So we would just have to rotate your, I guess, your plane, because I just made it going to the right instead of going downwards. But I mean, the same principles apply. Just up means right, down means left. So 91 key, root. Then to the right we have 105, 999, that's fine. Left of 91 we have a 9. We have left of that is a 4. Then right of 9 is a 56. And right of 56 we have a 71. Then right of 4 we have 8. So this is a successful tree, and we've added this tree, we've created this tree. We can do it manually, we can do anything we want, but yeah, that's the thing. We just add a number at a time, and each tree is added as a leaf. So let's get into some deleting, and let's look for the deleting an entire tree. Of course, if you say clear whole tree, you would just make a new node being the root, delete the root, and then root equals null and delete the node you just created. So that's simple. But let's go to remove node. So here we have the the public version, which would be called here, just entering the integer of what you want to delete. Then that calls the private function, this is the real function really. And so let's look at this code here. If the root isn't null, then you begin, and this links to, of course, this else, which is the tree is empty and there's nothing to delete. So of course there's no reason to even begin checking, because it's just a null tree. It's nothing in there. But if it isn't null, then we begin. So here our first if within this if is if the root key is equal to the key. So we look at the root key, and is it equal to the key that we inputted that we want to delete. So if we entered like 91, that would be here, and you would just call remove root match, and that would be take you to here. Then again you would say if root isn't null, you would start looking, and you would look for the smallest key on the right side, and this is where removing the root actually may be the more complicated one, because you want to remove that, but you can't not have a root. So what you do is, because you know that the smallest on the right side will always be bigger than everything on the left side, you can just take whatever's here and move it in. So what you want to do is you want to just you just want to basically swap these two. You swap it with the slowest, which is 105. But we can get to that one later. Let's first look at the simpler case, or maybe not so simple. But if it's not the root key, the text I wrote here is just basically it checks left and right recursively, because that just makes everything, I mean, this is why recursion is pretty much essential in dealing with traversal and creation and deletion of keys, because it very naturally it lends itself to trees, because trees kind of work with the bottom up. So you check left and left and left, but the actions kind of happen from the bottom up, which is what you want with trees. You want to work from the bottom, basically. So now we basically have we keep checking. So removing a node, you would keep checking until you find the node. Basically, yeah. So if you find the key, basically, you keep traversing the tree. First, you would look on if it's less than the thing, or if it's greater than. You would just keep checking, keep recursively checking on the left and right side. you traverse the left side. If it's smaller than, if the key you're looking for is smaller than the current key, then you move left, right? You call the remove node. But if you find the tree, if it's equal to it at any point, then you just call remove match. If you traverse the whole tree and you find that it's not equal to it, then you just say the key is not in the tree. And there you go. So we have two functions here for removing. We have removing the root and we have removing the node. So removing match. Let's move to remove root match, which is not the remove node. Oh, sorry, this is the root. Same thing for the root. I mean, if the root is null, then you just delete it and you've deleted the whole tree. If the root has no children, same thing. If the root has one on the right, you basically only one on the right. Basically, you shift the node from the right and all that stuff. So let's remove a match. If we have a match, let's take 56. Well, actually, let's take maybe 8. Let's delete 8 first. This has no children, so this is one scenario. Basically, the three scenarios are 0 children, it has 1 child, or it has 2 children. Those are the 3 options, because it can't be null, otherwise it will be an error. So let's remove this match. So here, doesn't have children, then it just deletes the node, and yeah, it just makes that current thing null. So that's pretty simple, right? Let's do that here. Just remove this and remove the link to it because it becomes null. And let's do it in our program. Let's just double check that we have. Let's just double check. Yeah, let's double check. We have our 8 isolated as a leaf, so let's delete that 8. Delete 8. So now let's view this. Simple as that. 8 is just not there anymore, and that's as simple as you can get. So that's what we have in our tree. 8 is just gone. Now let's look at the second scenario where we have 1 child, and left and right is the exact same thing, because it just checks the right side. If the left side is null and the right side is null, so if it has 1 child on the right, the way to check for this is the left is null and the right is not null. That means that there is something existing on the right side, but there's something on the left. So let's just look at this from a logical perspective. Let's delete 56. That has 1 right node, right? We want to delete 56. So the easiest way, if 71 had a bunch of children, it really wouldn't matter, because all you would need to do is bring 71 up, because 56 doesn't have a left node. So all you would have to do basically, you would have to delete this, and if you want to just connect it like that, or you could just make a new connection, that would happen. So let's test this. This is basically trying to delete, what was it, 56? So let's go here. 1 on the right. Let's double check that we have, oh wait, 8 still appeared. That's not right. Let's print the tree. Okay, wait. Let's just double check this. Oh, 8 wasn't deleted. Let's just double check this. Delete 8 again. That's what we have. Print it out. Okay, there we go. Now we want to just, so let me just delete, I think I have an extra file for some reason over here. That one had the 8, so let's just delete that. So we want to delete 56 now, and let's delete 56. And that's deleted. So what we should have is, it went from 9, 56, 71. It should move to just this. Oh, we have to, that's weird. Okay. I think I just had 2 files open. That's probably what was wrong. Let's just see. 8 doesn't exist. Oh. So let's delete 56. And let's print it out. And there we go. So we have, I think I have another text file of the exact same, like I have a bunch of copies. It's probably written the copies, that's fine. But anyway, yeah, so it deleted that, displayed it that way. And that's what our tree looks like now. 9, 4, and then 71 here. Okay, so now the final one really is having both children. So let's look at both children. If it has both children, it's just an else because obviously that's the only remaining option. We take, this is the remove match, yeah. We take the smallest on the right side, which is a function that we have to just find the smallest, which just traverses the tree to find the smallest one, to go left, left, left until there's no more lefts. And yeah, that's what we call here. Then we find if the smallest on the right side is greater than 0, then we remove the private node of that key, and then the match key becomes the right side. So in simpler terms here we have 9, and because we have to choose between that or that, the best one to choose is the smallest on the right side. We want to pick this side because we know that the right side is always going to be bigger than the left side. So if we move this up here, even if this had, say, a I don't know, 36 or something and a 50, for example, would move this up, and then we would double check that this isn't there. If this is there, then, oh wait, sorry, that wouldn't work. It would just become 36 rather. That's probably a bad example. So let's say this is 36. I'm going to remove that. We keep looking on the right side for the smallest number. So that's what we call this function. Smallest on the right side, we're just trying to find it, right? So we're not using 36, we're just using 71. So 71 is the smallest, so that becomes this number. And that's actually just erase that. So what we expect to happen would be we delete the link here, and we're deleting 9. That's the important thing we want to delete really. But 71 moves up there, so let's put 71 here, and that's really what should happen. So let's delete 9, which is this thing here. So let's delete 9. That says it's deleted. And what we have is we have 91, 74, 4, and 105, 4. And that's basically what we have. It's just kind of like a V shape now, but upside down. So then let's go back to what we had before, which I kind of skipped over because I just wanted to get to that last, is the root match, which is if the root key is the key you want to delete. So say you say you want to delete 91. Let's see what we have to do here. We call this immediately, nothing else to it because we found it. So this is remove root match. We have all these things, but the key thing is same thing. We have 3 situations, split up into an extra one because we have left or right, but left and right's the same thing. And on our tree we have a left and a right. So this would do the same thing as what we just did with the 9, where we check for the smallest. Sorry, 2 children, same thing. Check for the smallest on the right side, which would be 105, because if you put 105 there, we delete 91, then 105 is still bigger than everything on the left, and it's still smaller than everything on the right. That's really why you want to take the smallest on the right side, it's the easiest way. Another decent way of doing this would be taking the largest on the left side, but I mean at this point it's kind of preference, but I think the right side is a much better way of doing it because it's first of all it's easier, and actually that's probably the main reason. I think both can work because if you take the biggest on the left side, it'll be bigger than everything on the left side, and it'll be smaller than everything on the right side, so it should be fine. But the way I've done it in my program, I've taken the smallest on the right side. So let's just do that. Let's just delete the root node. Let's delete it. Root node was with key 91 was replaced with 105, and let's display that. Basically, let's see how it would happen. We want to let's escape that, and let's delete 91. But we take the smallest on the right side, which is that. Let's just delete this whole thing so it's easier to read. Then we write the text 105. Then we create a little link here. So it goes here. So basically that means that 105 remains to be a correct, it fits everything perfectly, and that's all you need to do is take the smallest one, because the right side is bigger than everything on the root node. That means it's guaranteed to be bigger than anything on the left side. And the right side is obviously it's smaller than everything on the right side. So this works, and our program also agrees with this. So now let's just quickly go through traversal. Let's go back to the original one. I'm actually just gonna, it might be, because we have so little nodes here, let's just actually return back to our original numbers tree. Let me just copy this. Oh, that's too many numbers. Let's just quickly change numbers to being what we had originally. So we had, where is it? 91, 9, 4, 56, 8, 9, 9. Let's just save that, and let's relaunch this, and this should just give us the original tree of what we had. Yes, okay. Maybe I can just go all the way back. Oh, I think this is what we had. Let's double check. I don't know. We stuck on this for too long, but let's just get back to original so we have actually some more stuff to traverse. Now we've done with deleting. We have 71. Okay, that's how it should be. Okay, this is how it's originally, and we have basically we have three options. We have in order, which is LNR. Then we have pre-order, which is, I think it's NLR, and then we have post order. This is just ways of reading the graph, the tree. And we have LRN. So basically, the reason why these are called this way is because in order is you check the left, then you take the node, then you check right. Pre-order, you check the node first, which is why it comes early, because if you look at it in order, it goes all the way down to the bottom, takes it, then it goes right, then it takes it. So that in order ends up being ascending order. So you don't have to write an ascending order function because in order already does it for you. Then you have pre-order, which is NLO, so that ends up, like, you'll print 91 first, which obviously won't give you any kind of ascending order type thing. Then post order, of course, you finish off with the node, and that's what we have written. Well, let's just bring this up. Same thing here. We have LNR, NLR, yeah. So let's take a look at this. You take the left node, and really, let me just write this down to maybe just have a brief thing. You first check the node, then you go left. Check the node. Does it have a left? Yes. Does it have a left? Yes. No. Doesn't have a left. So then you just take the node and then you go right. so that maybe didn't help. But yeah, we go left once. Does it have a left? Yes. Does it have a left? No. Then we go N, so that's 4. Then we go right, because it doesn't have a left, or I've done the node already. And then we put 8. Then we traverse back up because we've already done these. We check 9, we've already gone past that path, so we're just doing the 9. Then we go right. Does this have a left? No. Then we just print 56. We go right again because we've printed the node now. Then we go R. Then we go 71. So now, since we've done everything on the left side, we just traverse right back up to 71, and now we print N because now we're finally done with the left. We've done the left side of 91. So 91. Same thing. We check right again because we've done the node. We've printed N, so now we go R. That's what we have to do next. Then we go this L, nothing, so we go 105. Same thing with this L, nothing, so N, and we have 999. And we can confirm this by using post pre-order. It's just ascending. That's the best way to actually. This is easy to test if you're doing it right. It's just ascending order. So let's do pre-order, where we go node first. So immediately print the node. Then you check left. Then you print the node. Then you go right. Well, let's double check this. Oh yeah. Okay, so you do node then left. So node left. So let's put this in line with this. Yeah, it's all about the lettering. So it's node left. If there's a left, then you go node left. So node left, nothing. We've already done node, so let's go to 8 because we've already we can't just write 4 again. We've already done that. So we've done these two, and now we've done 9. So now we've done left, we've done node, now we go to right. Then we immediately print node. Then we go left, no left. Let's go right. Let's print node. Then we go all the way back up here. We've printed node, we've gone left. Now we go right. Print node immediately. 105. Left, no left. Let's go right. Print node immediately. And there's nothing else to do here. And let's double check with this 91, 9, 4, 8, 56, 71, 105. There we go. And now we go post order. This one, you go left. So you always want to restart the LNR check again. That's important, the LRN. So we check left, is there left? Left again, left. Then we go right, and then we go node. And because we've already checked there, we're going backwards now, so it's just easy now. And then we go back here. We've done left, we haven't done right, because right has to come first. So we go right. We go right, then we check left, no left, we go straight to right, 71. Then we go back, because now we're going backwards along the same path, so that's simple. 9. So now we back up to here, we've done left only. We don't do N yet, because we have to do R still. So we go R, left, nothing, we go right. Then let's go 999. Then we go back up, we're going up, back up, so we've already tested this, so we know that's the last one. And the root should always be last in this situation, I assume. And then let's check this. 8, 4, 71, 56, 9, 999, 105, 96. And that's just the basics of a tree. We've added trees, we've deleted nodes, and that's the key here. And when it comes to coding, let's look at the code and compare it to what we did here. The code needed for these traversals are actually very simple because of the convenience of recursion. So we looked at if the root is null, that's always going to be your check. Then we say tree is empty. Else, if it's NLR, because we print the node first. This is pre-order. Print the node first. We immediately print the node. Then we recursively call it left. And prints the node again, goes left. Prints the node again, goes left. Until it's done on the left side, then it goes right. and that's as simple as it is. That's just the order that you recursively call it. You recursively call the left and right for all of these things, but this one is n, we can call that n. This is L, because you're recursively checking left, because that's where it is. If you look here, you're not really doing anything with left, you're just checking left until you've stopped, basically. And then you go right. So that's basically what all it is, really. Then same thing for here, except the order is just changed. It's the exact same thing, it's just the order. So for this one you go left, then you go key, which is N, and then you go right. So LNR, geez. Then this one you go LRN, and that's about it. So N order is ascending order. So and that's why it's called ascending order. The best function for these types of trees, really, as opposed to other things, is for keeping track of things that are constantly being added and removed, like locations in maps. That's a very common thing, or setting functions where you want to keep on setting data points, because it keeps things tracked of where you put them. Like 71, it's weird how 71's here, and we've got 8 there, we've got 105 here, because they're all added as leaves. Like they're all added as a leaf. So there's if you add an item, let's say we add 35, it's always going to be a leaf, because it's going to go left, right, left. So it's going to go here. It's always going to be like by itself. So you can keep track of when they were placed, and you can keep track of its order. So it's also good for keeping track of numbers, names, to keep track of, you can keep a tracker of the data was placed in the tree, but also keep track of, you know, where it is and what the order is. So maybe like a kind of yellow pages. And yeah, that's basically, that's trees, and boundary search trees in particular. So I hope you found this clear and easy to read. And this code is, the source code is not really that important, because I just added a bunch of things and insert numbers. And so yeah, so the reason why I used private and public is because I didn't want source to be bogged down by using nodes. So there's no nodes in this source file. But yeah, there you have it.